actual properties, and major constants in the multiverse structure. Our universe is only one among several, each rising up out of various introductory conditions and governed by its own set of actual regulations. The possibility of a multiverse arises naturally from certain interpretations of quantum mechanics and cosmological expansion hypotheses. According to inflationary cosmology, the rapid, dramatic expansion of spacetime in the early universe might have prompted the development of pocket universes within a larger multiversal scene. Each pocket universe would have its own unique properties formed by arbitrary quantum fluctuations during the inflationary epoch. While the multiverse speculation remains theoretical and hard to test observationally, it offers a compelling answer to the fine-tuning problem in cosmology, the apparent unlikelihood that the essential constants of nature are finely tuned to allow for the existence of complex structures, such as galaxies, stars, and life itself. Another captivating idea that challenges conventional ideas of astronomical origins is that of eternal inflation, proposed within the framework of inflationary cosmology. Eternal inflation suggests that the universe undergoes a perpetual cycle of inflationary stages, each resulting in new regions of spacetime with potentially different physical regulations. In this scenario, our observable universe is only one of countless regions within a continuously expanding cosmic foam. The idea of eternal inflation raises significant questions about the nature of time and causality in the multiverse. If inflationary bubbles generate new universes endlessly, then the concept of a singular beginning or ultimate start becomes increasingly elusive. Instead, the universe appears as a dynamic and ever-evolving entity embedded within a larger cosmic fabric of inflationary growth. In recent years, advancements in theoretical physics have further spurred interest in alternative cosmological models that challenge the traditional account of cosmic beginnings. For example, some researchers have explored the plausibility of a cyclic universe, where the Big Bang is not a singular event but rather one phase in an endless cycle of cosmic expansion and contraction. According to cyclic cosmology, the universe undergoes successive cycles of creation, evolution, and destruction, each culminating in a big crunch followed by a new Big Bang. The cyclic universe hypothesis draws inspiration from ancient cosmological ideas and modern theoretical frameworks, such as string theory. Within the framework of string theory, which posits that fundamental particles are not point-like objects but rather tiny vibrating strings of energy, the concept of a cyclic universe arises naturally from certain configurations of the theory. String theory suggests that the universe may exist in a higher dimensional spacetime, where cycles of expansion and contraction are a natural consequence of the interaction between fundamental forces. While the cyclic universe theory remains speculative and faces significant challenges in terms of observational evidence and theoretical consistency, it represents a bold attempt to reconcile quantum mechanics with general relativity on cosmological scales by proposing a continuous cycle of cosmic renewal. Cyclic cosmology offers an enticing possibility of a universe without a definitive beginning or end, where each cycle builds upon the remnants of its predecessor. In addition to theoretical frameworks, observational cosmology has also provided crucial insights into the early universe and its evolution over cosmic time. The discovery of the cosmic microwave background, CMB, radiation in the mid-20th century provided compelling evidence for the Big Bang theory, offering a snapshot of the universe when it was only 380,000 years old. Precise measurements of the CMB by satellites like the WMAP and Planck observatories have enabled scientists to map variations in temperature and density across the early universe with exceptional accuracy. Furthermore, observational cosmology has shed light on the large-scale structure of the universe, revealing the intricate web of galaxies, clusters, and cosmic filaments that span billions of light-years. By studying the distribution of galaxies and measuring their redshifts, cosmologists have been able to trace the growth history of the universe and infer its age, composition, and fate. One of the most remarkable discoveries in observational cosmology is the existence of dark energy, a mysterious form of energy that pervades the universe and is driving its accelerated expansion. First inferred from supernova observations in the late 1990s, dark energy constitutes about 68% of the total energy density of the universe, making it the dominant component of the cosmic energy budget. The existence of dark energy presents a significant challenge to our current understanding of fundamental physics, as its origin and nature remain poorly understood. Some theories suggest that dark energy may be a manifestation of the vacuum energy predicted by quantum field theory, while others propose modifications to Einstein's theory of general relativity to account for the observed acceleration of the universe. In parallel with observational efforts, experimental physicists are actively searching for new particles and interactions that could provide clues to the fundamental nature of dark energy and other cosmic mysteries. Projects such as the Large Hadron Collider, LHC, aim to probe the frontiers of particle physics by colliding protons at unprecedented energies, potentially revealing new physics beyond the standard model. Moreover, advances in astrophysical instrumentation have enabled scientists to explore the universe across multiple wavelengths of the electromagnetic spectrum, from radio waves to gamma rays. Observatories such as the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope have revolutionized our understanding of star formation, galaxy evolution, and the cosmic distribution of dark matter. Looking ahead, the next generation of observatories, such as the James Webb Space Telescope, JWST, and the Square Kilometer Array, SKA, promises to unlock new insights into the early universe and its fundamental constituents. These cutting-edge instruments will enable scientists to study the first galaxies, probe the epoch of reionization, and search for signatures of primordial gravitational waves left over from the Big Bang. In conclusion, the quest to understand the origins of the universe represents one of the greatest intellectual challenges of our time. From ancient myth and philosophical inquiries to modern scientific theories and observational discoveries, humanity's exploration of cosmic origins has yielded profound insights into the nature of reality itself. As we continue to push the boundaries of knowledge and exploration, new theoretical frameworks, observational techniques, and experimental technologies will undoubtedly shed light on the fundamental mysteries of existence and our place in the universe. Initially, there was a vastly dense mass of matter. This mass underwent an explosion that led to the formation of particles, atoms, stars, and galaxies that we can observe today. For many years, this has been the explanation offered by physicists. However, recent research has introduced a new perspective that suggests the universe doesn't have as early a beginning as initially believed. Rather, it could be part of a recurrent cycle in which the universe goes through a series of cycles of expansion and contraction, potentially in an endless loop. Brian Cox, a renowned physicist, casts doubt on the Big Bang theory, arguing that something cannot arise from nothing. This questioning adds an intriguing element to the discussion. Additionally, research from the James Webb Telescope has uncovered information that contradicts the idea that the Big Bang marked the absolute beginning of the universe. This leads to the fundamental question: if the Big Bang was not the beginning of the universe, then what was? Join us on this journey to the origins of the universe, where we will explore the frontiers of the Big Bang and answer this question and many more. If you are interested in staying up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification bell. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the Big Bang theory. According to this model, the universe was much smaller, hotter, and denser than it is today, approximately 13.8 billion years ago. During that period, all the elements that make up our world were formed in a matter of minutes. In this theory, our universe, including stars and galaxies, was once as small as a peach and had an incredibly high temperature of over a quadrillion degrees. Interestingly, this astounding account aligns consistently with all current observations. Astronomers have examined everything from the remnant electromagnetic radiation of the early universe to the abundance of the lightest elements and have found that everything agrees with the predictions of the Big Bang. To the best of our knowledge, this description fits the reality of our universe perfectly. However, despite its apparent power, we know that the Big Bang theory is not the complete picture. There's a missing piece of this puzzle, and that piece is an understanding of the initial moments of the universe. This challenge is due in large part to the limitations of the physical theories we currently use. The combination of general relativity and high-energy particle physics gives us a significant conceptual framework. However, as we delve deeper into the initial moments of the universe, the mathematical complexity increases significantly, reaching a point where our current methods cannot provide meaningful solutions. One sign of this difficulty is the presence of a singularity, a point of infinite density, at the beginning of the Big Bang. This concept suggests, literally, that the universe was once compressed into an infinitely small and dense state, which seems implausible. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provides a more complete understanding of the universe's first moments. Our current tools and theoretical frameworks are not robust enough to address this challenge, so we need to develop new physics that can encompass and explain gravity and the other fundamental forces at extremely high energy. This is precisely where string theory comes into the picture. This theory seeks to be a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. Essentially, string theory posits that it can provide an explanation for the initial moments of the universe. Within string theory arises the concept of an eon, which takes its name from the Greek word meaning age or era. This idea suggests that the Big Bang, as we know it, was the result of a prior event, implying that it was not the absolute beginning but perhaps a part of an ongoing process. Expanding the concept of an eonic universe has led to the development of other speculative ideas such as the multiverse and brain cosmology. These ideas introduce alternative explanations for the origin of the universe and its structure, which could provide the missing piece to the puzzle. In conclusion, the understanding of the universe's beginnings has evolved significantly since the initial proposal of the Big Bang theory. While the theory remains powerful and consistent with current observations, it does not provide the full picture. New physics, including string theory and the concept of an eonic universe, offer exciting possibilities to further our understanding and explain the universe's first moments.